Jnanam paramam dheyam. Knowledge is supreme.
So, we have arrived at more questions than answers by using different basis sets, right. That is what we have got so far, okay. But have you at least understood what we have written? Now, we will try to not prove, but at least know the answers to the questions that have come to our mind, okay. To do that, one needs to use group theory. Using group theory, you arrive at what is called the great orthogonality theorem. So, as you have understood by now, anything that has words like great or golden, they are bound to be very useful, right. Great orthogonality theorem is also called great for a good reason, okay. And using great orthogonality theorem, we arrive at what are called character tables, things that you have already used in this inorganic course in the last semester, I believe, okay. So, what we are trying to do is, we are in this course, we do not have the scope to derive great orthogonality theorem, but what we will do is, we will show you 5 consequences of it, and from there we will at least learn how to derive character tables. And I will not ask you to derive character tables in the exam, but unless we do the derivation of 1 or 2 character tables, we do not understand anything. We do not understand what they mean, okay. That is why we are even discussing this, okay. So far so good, we go ahead. Now, if you look at this great orthogonality theorem, of course, I should paraphrase it a little bit for you. What these gammas mean, this is capital gamma, this is not tau. Some people call it tau by mistake, it is not tau, it is capital gamma. Gamma I of R Mn. What does this mean? It means the Mn element of the transformation matrix corresponding to symmetry operation R in the ith irreducible representation. Ith means let us say I have 5 irreducible representation, I can be 1, 2, 3, 4, 5, okay. I will say it once again. Look at this, gamma I of R Mn, what it means is the Mn element of the transformation matrix of symmetry operation R in the ith representation. Have you understood what this means? Have you understood what it means? Let us say I have some representation, say E will be there anyway, R1, R2, so on and so forth, something R, no I will not write, I will just leave it at R there. So, these are the symmetry operations, and I have these irreducible representations gamma 1, gamma 2, so on and so forth. Let us say gamma I. Understood? What is this? What is this matrix? It will be 1, 0, 0, something like that, 0, 1, 0, so on and so forth, and finally you will have 0, 0, 1. I have not defined what the dimensionality of this matrix is. Dimensionality of the matrices in a representation is the dimensionality of the representation itself. So, dimensionality of these matrices is 1. So, 1, 2, 3, these representations are one dimensional representation. Dimensionality of the matrices here is 2, so it is called a 2-dimensional representation. Whether it is reducible or irreducible, that will come later, okay. But here what we are saying is that suppose we know all the reducible representations and I make a chart of them. Then I can write these matrices for all of them. Now let us say there is something like this, x1, x2, so on and so forth, y1, y2, so on and so forth. Look at this element. In this matrix, what would you call it? This is the 1 1 element, this is the 2 2 element, right? What is this? And this 2 1 and 1 2, right? And in fact, in different books they actually use different notations as well. But let us agree on one. What is this? 2 1 or 1 2? 1 2, and this is 2 1. Okay. So this 2 is m, 1 is n. In this case, what is m? What is n? M is 1, n is 2. So understood then? Now does this make a little more sense? Gamma I R mn means the mn element of the transformation matrix of the symmetry operation R in the ith, remember, irreducible representation. Now have you understood what this means? Not the entire thing, only this. Understood? What have I done here, or what has been done here? Take this, multiplied by the complex conjugate of another matrix element of another representation, alright, m dash n dash element of symmetry operation R in the jth irreducible representation. So you multiplied one matrix element of an irreducible representation by the complex conjugate of another matrix element of another irreducible representation, and you have summed over all values of R. Okay. So you have done this operation for E, you have done it for C2, you have done it for sigma V, you have done it for sigma V dash if we are talking about C2V. Understood left hand side? If you have not understood the left hand side, please raise your hand now. Can I go ahead? You understand what I have done? On the left hand side, I had just multiplied a matrix element, some matrix element of the ith irreducible representation by the complex conjugate of another matrix element of the same symmetry operation R from a different irreducible representation, and have summed over all values of R. Right hand side is H divided by square root of Li Lj, where Li and Lj are the dimensionalities of gamma I and gamma j, dimensionalities of the ith and jth irreducible representations respectively. Okay. So H by root over Lij. What is H by the way? What is H? H is called the order of the group. For our purpose, order of the group means total number of symmetry operations. Very important to remember this. Total number of symmetry operations, not total number of symmetry elements. Is going to make a difference later on. In case of C2V, what is the total number of symmetry operations? 3 or 4? How many say 3? Okay, how many say 2? This is becoming like a bidding. What is the total number of symmetry operations in C2V? The correct answer is 4. E, C2, sigma V dash. These are all symmetry operations, right? Okay. 4. For C2, I can rotate once and I can rotate twice, right? Once, twice. Is that one operation or two operations? Actually, one associated with C2, because C2 square is equal to E, that is a different symmetry operations. Let us not forget that. Okay. Another quick quiz. C3V. We have done ammonia, C3V. What are the symmetry elements? Symmetry elements, what are the symmetry operations? E of course has to be there, C3 is there, and 3 sigma V's are there. Is there anything else? C3 square is also there, isn't it? C3 square. These are the 3 bonds. The problem is Yeah, right, C3V. So, this is C3, this is ammonia. Turn once, start with what is this color? Green, green on the top, right? I turn it once, blue comes on the top, this is blue, this is not green, even I can see that. Yeah, blue on the top, right? I turn once again, it is white on the top. So, how many symmetry operations would that be? Leaving out E. When white comes on the top, that is 1, right? But this C3 and C3 square, or we started from here, we are supposed to start from here, right? This is C3, this is C3 square. What else can we do? I can start it with this, I can do this as well, right? Minus. So, how many symmetry operations associated with C3? Not 1 but 2. Yes. We are doing the same process of rotating. So,
can we consider all of them to be the same?
No, we cannot. That is what I am saying, because that is why I have used chalks of 3 different colors.
For example, we are talking about the green, sigma we are talking
Yeah.
about, and over the C2, which is rotation we are talking about. So, our rotation.
So, C2 is with respect to an axis, sigma v is with respect to a plane. So, there is no confusion in your mind that they are different. But C3 and C3 square are performed with respect to the same axis, not only axis, same axis. That is why you are confused whether they are 2 or whether they are 1. Have I got the problem right? They are 2 because they lead to different configurations. When we talk about configurations, you would have studied in stereochemistry something. So, let us call this A, well, W, B and G. This is the configuration you start with. You rotate, it is GWB. Rotate the other way, it is BGW, all different configurations. Okay? So, C3 plus C3 minus, or what you can call C3 and C3 square, are different symmetry operations. This part is important to understand, otherwise we will get all our calculations wrong later on. Okay? Are we clear? So, how many symmetry operations are there in C3V? Yes? E, C3, C3 square, then sigma V number 1, sigma V number 2, sigma V number 3. Okay? 6. So, what is that? 6 is H for your what is it called? C3V. So, what we have learnt is for C2V, H is 4, H is 4, right, for C3V, C2V. For C2V, H is 4, E, C2, sigma V dash. For C3V, H is how much? 6, E, C3, C3 square, sigma V number 1, sigma V number 2, sigma V number 3. So, now are we clear what H is? H is called the order of the group. It is equal to the total number of, please do not forget this, symmetry operations. It is not the total number of symmetry elements, symmetry operations. Okay. So, we are trying to understand the right hand side. I should change the title of this module. It is group theory, great orthogonality theorem, GOT. It is not a goat, it is got. A is not there, great orthogonality theorem. Alright. Now, and then, so on the right hand side, left hand side we have understood, right hand side we have H divided by square root of Li Lj. Li Lj are the dimensionalities of ith and jth irreducible representations respectively. Clear? Now, what else do we have multiplied by it? Delta Ij, delta mm dash, delta nn dash. You know by now, by virtue of having done quantum chemistry, quantum mechanics courses, what is the meaning of delta? What is delta? Suppose delta Ij, what does that mean? simple mathematical answer.
So it can be either 1 or it can be 0.
When is it 1, when is it 0? So it required a collaborative effort. One of them gave half the answer, the other gave half the answer at the same time. So both of you are right, very good, full marks. So when I equal to j, then delta ij equal to 1. When I is not equal to j, delta ij equal to 0. Okay? Same is true for delta mm dashed and delta nn dashed. Okay? Now, since we have now understood all the terms, all the factors in this equation, I hope we now appreciate why it is called an orthogonality theorem. You remember what orthogonality is? Or rather you remember what orthonormality is? Integral over all space, product of two vectors is equal to some value when they are the same and 0 when they are different. That is orthonormality, right? So, what great orthogonality theorem leads us to is that if you are working with irreducible representations, then the matrix elements of these irreducible representations behave like a set of orthonormal vectors. Okay? Are we convinced that that is what the great orthogonality theorem means? Okay? But this also is only for the purpose of knowing where everything comes from. What we are really going to use is these 5 important working rules that arise out of this great orthogonality theorem. We are not going to derive the rules either. If you are interested in the derivation, please look up Cotton's book. Okay? Cotton's book does not give you the derivation of great orthogonality theorem as such, but it does give you derivation of these 5 working rules from great orthogonality theorem. They are pretty straightforward, you can go through them. We will not ask questions on that in this course. These are the 5 working rules. As we will see tomorrow, using these 5 working rules, we can work out the character tables of whichever point group we want. That is what we will do tomorrow. But today, before we close, just one point that I want to make is this. What is the character of the matrix standing for E in the one dimensional representation? That might sound like an idiotic question, but please bear with me. You remember what character is? Trace, sum of all the diagonal elements. What is that character for the transformation matrix of E for a one dimensional representation? Has to be 1, cannot be anything else, there is only one number anyway. What is it for a 2 dimensional representation? 2. What is it for a 5 dimensional representation? 5. What is it for a 232 dimensional representation? Okay, that is kind of too much of an exaggeration. The point we are trying to make is this, and this is something that is not written in those 5 rules, so I will write it separately. Chi is how we denote the character. Okay. Chi for E identity operation for the ith irreducible representation is equal to the dimensionality of that representation. Do we agree with this or do we not agree with this? Chi I of E is equal to Li. This is a very simple rule that we can understand very easily, right? Character of the unit matrix for the ith irreducible representation is equal to the dimensionality of that representation. Let us remember this. Tomorrow we are going to take these this and the 5 working rules axiomatically, and we will work out character tables of C2V and then C3V.